Hi and welcome. This is the 6th tutorial in an advanced C# course, and this is the first part of a video series on asynchronous programming using the C# programming language. In this video, we'll look at an overview of asynchronous programming in C# with a particular emphasis on Microsoft's recommended approach to using asynchronous programming for new development. Microsoft's recommended approach to including asynchronous behavior in new applications is to use the Task-based Asynchronous Pattern, TAP. The two legacy methods for providing asynchronous behavior are Event-based Asynchronous Pattern, EAP, and Asynchronous Programming Model, APM. The Event-based Asynchronous Pattern will not be discussed in this video series, but if you wish to learn more about this legacy pattern, please navigate to this URL. We have already covered the Asynchronous Programming Model, APM, in the advanced course. In part 3.5 of this course, we looked at using a callback method and a built-in delegate to implement asynchronous behavior. Please navigate to this URL to view a video released on this channel that covers the Asynchronous Programming Model, APM. As always, all links mentioned in this video can be found below in the description. Later on in this tutorial, we'll look closer at how using the task-based asynchronous pattern can result in asynchronous behavior for our applications and ultimately ensure that our users have a smooth user experience when using our applications. For more videos on advanced C# topics and much more, please consider subscribing, and please ring the bell so that you'll be notified of future videos released from this channel. Right, so TAP, or Task-based Asynchronous Pattern, is the recommended design pattern for creating asynchronous behavior for new development. C# version 5 produced a simplified approach to asynchronous programming that leverages asynchronous support in the .NET Framework 4.5 and higher, .NET Core, and the Windows runtime. .NET Framework 4.5 or higher and .NET Core contain many members that work with async and await. These members can be identified by their names, which contain an async suffix. So what gave rise to the task-based asynchronous pattern? We live in an age where our applications should not only run on desktop computers and notebook computers, our applications in a lot of cases will also need to run on smaller devices. For example, handheld devices like tablets and mobile phones. These smaller devices may not have the powerful resources that desktop computers and notebook computers have to handle resource-intensive operations. So, an operation like, for example, downloading a large document from a remote server may ultimately result in poor performance of our applications. A poor UX, or user experience, with our applications can cause user frustration and cause our users to take a dim view of our applications. Implementing this pattern in our code can result in a smoother UX, user experience. The code is easy to implement, and even though the code results in asynchronous behavior, the code can be written in a synchronous way. We'll look at a code example to further elucidate this point in a bit. The C# compiler makes it very difficult for a developer to implement the task-based asynchronous pattern incorrectly. For example, in an IDE like Visual Studio, red squiggly lines will appear in appropriate regions of code if the relevant asynchronous code has been written incorrectly. Messages will also be made available to the developer from the C# compiler in Visual Studio to guide the developer on how to fix the incorrect code. So, how can long-running operations result in a poor user experience with our applications? Say, for example, a button is clicked, and within the event handler method of the relevant button click event, a long-running operation is invoked. If this operation were to be invoked synchronously, the thread of execution on which the relevant time-consuming operation is running is blocked until this long-running operation has completed. While the relevant thread is blocked, the application is unresponsive, meaning the user cannot perform other operations with the application until the long-running operation completes. So this ultimately results in poor user experience with our application. There are two kinds of blocking operations: CPU-bound operations and I/O-bound operations. So let's look at CPU-bound operations. This occurs when an intensive computation needs to be carried out by the device's CPU. For example, you might have a game running, and a single action from the user may cause multiple characters in the game to incur damages. The calculations of these damages may be CPU intensive. An operation like this, if done synchronously, can result in the UI to freeze or stutter. Running the calculations in parallel across multiple cores can alleviate this and make the UI, or user interface, perform smoothly and responsively. So the developer could use the task.run method to run calculations in parallel to alleviate the effects that handling these computations synchronously could have on the user's experience. Other examples of applications that may need to run intensive CPU-bound operations could be financial or scientific applications. So let's look at I/O-bound operations. I/O-bound operations are performed when requesting data from a network, accessing a database, or reading and writing to a file system. The blocking effect during an I/O-bound operation causes the CPU to wait for the relevant I/O-bound operation to complete. So the CPU will need to wait, basically lie dormant, while, for example, information is retrieved from an Azure SQL database that resides in the cloud. Once the information is retrieved and, for example, appears in local memory, the information can then be processed by the CPU. The CPU can only then continue processing other instructions. While the I/O-bound operation is running, the CPU is blocked from running any other operations. Performance will not be optimal for our applications when the code for these relatively long-running operations are handled synchronously. I/O-bound operations are the most common encountered blocking operations. So we are going to focus on resolving the blocking effect of I/O-bound operations through the implementation of the task-based asynchronous pattern in this video. Note that generally speaking, I/O-bound operations are far slower than CPU-bound operations. In business applications, I/O-bound operations will be far more common operations that will be encountered and should be handled asynchronously. And let me emphasize, I/O-bound processing is far slower than CPU processing. So let's look at a basic code example. We won't implement this particular code in Visual Studio. This code serves to give us a general idea of what the task-based asynchronous pattern looks like in C# code, and we'll also get an idea of how it works. Let's first look at the synchronous version of this code example. We'll then modify the code so that it is implemented using the task-based asynchronous pattern. So in this synchronous version of the code example, we have a high-level button-click event handler named button_click. When the user clicks the button that invokes code within this event handler method, a call to a method named getDocumentContent is made. This method accepts an argument, which is the name of the remote file that our code needs to retrieve and process. So let's say that the path of the remote document is handled under the hood, as it were. A relatively long-running operation is encapsulated within a method named getDocumentContent_as_string, which is invoked within the getDocumentContent method. The long-running operation in this case is downloading a document from a remote server. After the long-running operation completes, a string is returned from the getDocumentContent_as_string method containing the relevant document content. A method named saveDocumentLocally is then called, which, as the name suggests, saves the content returned from the getDocumentContent_as_string method to a local file store as a new file. The document content is then returned to the calling code from the getDocumentContent method. Once the getDocumentContent method completes and returns the content to the button-click event handler method, the content is subsequently displayed to the user. This is denoted by a call to a method named displayContent. So while the code is performing the relatively long-running operation executed by the getDocumentContent_as_string method, the thread of execution on which this operation is running will be blocked, leaving the CPU idle until the getDocumentContent_as_string method completes and returns a value. So let's say that we are in luck and there is an asynchronous version of the getDocumentContent_as_string method available to us named getDocumentContent_as_string async. Note that this version of the method has the same name as the synchronous version, with the exception of the async suffix added to the end of the method's name. Adding the async suffix to the end of an asynchronous method's name is a naming convention used for asynchronous methods that are part of the implementation of the task-based asynchronous pattern. So the method we want to call is named getDocumentContentAsString So we need to use the await operator preceding the method call to the getDocumentContentAsString method like this. This is telling the C# compiler that we wish to call this method asynchronously. If any of our method calls within the getDocumentContent method are awaitable, as is now the case here, where we are using the await operator, we need to include the async modifier in the method signature of the method where one or more asynchronous method calls are invoked, which, as stated, is denoted by the await operator preceding the relevant asynchronous method being called. So let's include the async modifier in the method signature for the getDocumentContent method. Let's also adhere to the correct naming convention, so let's rename the getDocumentContent method to getDocumentContentAsync like this. The getDocumentContentAsync method will return a string value once the async method has completed, but when it is first called and hasn't necessarily completed, a generic task object will be returned. I'll elaborate on what the task object and the generic task object is in a bit. So we must include the relevant generic task type in the method signature of the getDocumentContentAsync method like this. We are calling an asynchronous method from the button click event handler named button_click. So we need to include the await operator preceding a call to the getDocumentContentAsync method like this. We are now calling an awaitable method within the button_click event handler method, so we need to include the async modifier within the method signature of the button_click event handler method like this. We don't need to include a task type in the button_click event handler method signature because it is a high-level event handler. All asynchronous methods that are not high-level event handlers like the button_click event handler will return a task object if the relevant method does not return a value, or a generic task object if the relevant method does return a value, as is the case with our getDocumentContentAsync method, which returns a string. So, for example, the getDocumentContentAsync method returns a string value once it has completed. So to reflect that this method is an async method that returns a string value, we include the generic task type in its method signature, and this generic task type accepts the string data type as its argument. So basically, the new asynchronous implementation of this example code means that when asynchronous methods are called with the await operator, the control is immediately returned to the calling code, meaning that the thread of execution on which it is executed is free to process other operations while the asynchronous method is running. So the CPU is not left idle while an I/O-bound operation is underway, as is the case in this example where a file is retrieved from a remote server. In this asynchronous implementation, the CPU thread of execution on which the relevant, relatively long-running operation was invoked can be used to perform other operations while the remote file is being retrieved from the remote server. In this case, the UI thread is the thread of execution. So if, for example, the user needed to execute a different button click event, another operation could run concurrently to the long-running operation invoked by the getDocumentContentAsString method. This means the user's experience with the application will not be negatively impacted by this relatively long-running operation. The user experience is not adversely affected by the relatively long-running operation performed by the getDocumentContentAsString method. So when the getDocumentContentAsString method is called, a generic task object is returned immediately to the calling code. The string value that is returned only once the getDocumentContentAsString method completes is returned at that point of execution in the code, but at a later time. While the relatively long operation invoked by the getDocumentContentAsString method is running, other operations can be performed by the user without negatively impacting the user's experience with the relevant application. Basically, the task object is a state machine. If you'd like a comprehensive explanation of what a state machine is, please navigate to this URL. The task object encapsulates information about the asynchronous process and either delivers the final result back once the asynchronous method completes or throws an exception if an exception occurs within the asynchronous method. So we can put traditional try-catch code around the call to our asynchronous methods as if the methods were synchronous to handle exceptions that may occur in our asynchronous methods. So when the awaitable method is executed, a task object is immediately returned to the calling code. The string value is only returned later once the awaitable method completes. When the task object is returned, the relevant thread of execution is then immediately released to the caller. The thread of execution is not blocked while the asynchronous operation is running. So the async method first returns the task object, in this case a generic task object, that promises to return a string value at this point in the code once the operation performed within the relevant async method has completed. This model is known as the promise model of asynchrony. If you wish to read more about the promise model of asynchrony, please navigate to this URL. On the C# side of things, the C# compiler transforms your code into a state machine that keeps track of things like yielding execution when an await is reached and resuming execution when a background job has finished. The async modifier is doing two things. Number one, it is a message to the C# compiler that this method can use the await operator inside it. The await operator designates the suspension points in the execution. Number two, the method itself can be awaited by methods that are calling it. The async modifier also is a message to the C# compiler that the method can be called asynchronously using the await operator. The await operator is telling the compiler that the execution of code cannot continue past this point until the awaited method has completed. So in the meantime, control returns to the caller of the method, which is the UI thread in this case, which allows, for example, the user to click other buttons while the incomplete asynchronous task is still running. Under the hood, as it were, when you compile your code through Visual Studio, the C# compiler rewrites your code into intermediate language, splitting apart your async method calls into lots of callback methods. So we as coders don't need to worry about the complexity of implementing callback methods ourselves. With this explanation, I'm admittedly, in the interests of brevity, glossing over a mass of complexity involved in making this asynchronous abstraction model work. For more detail and a comprehensive diagram of how the underlying framework is handling the asynchronous code, please navigate to this URL. Note that the line of code that includes the await operator is in fact doing two things. It is returning a task object when it is first invoked, and then later, when the asynchronous operation completes, it is returning the value returned by the relevant method, in this case, a string value. So we can write the code like this to make this clearer. We could first assign the task object returned by the relevant asynchronous method to a variable of type task. This is done without the await operator. We can then call the relevant task object with the await operator later in the code. In this case, the string value will be returned from the task object when the relevant operation completes. In this particular example, we can write what is achieved by two lines of code here in one line of code like this. So let's put the code back to how we originally had it. So let's create a code example. We are going to create two .NET projects. One project will represent the calling client code, i.e. the code that will contain the user interface. The other project will represent the server-side code. The calling client will be implemented as a UWP project or Universal Windows Platform project. The server-side code will be implemented as a Web API project. This example is very basic. We'll implement a button-click event handler on the user interface, which will be included within the UWP project. Code within the relevant button click event handler will asynchronously call a method included within the Web API server-side component. In the relevant Web API action method, we'll deliberately implement a delay to represent a task that is relatively time-consuming and should be awaited by our client code, i.e., should be called asynchronously. We'll implement another button click operation on the UWP project's user interface, which will implement code that runs a much faster local operation. We'll run the code and demonstrate that when clicking the button that kicks off the time-consuming operation implemented in the Web API code, that this does not impede the user's experience, and the user is able to click the second button, which carries out a much faster local operation. Perhaps the user can click this several times while the application is awaiting for the more time-consuming operation carried out on the server side to complete and return a value to the calling client code. We'll prove that the fast local operations can run concurrently while longer asynchronous operations are running in the background. And because we have written the long-running operation to run asynchronously, that the user's experience is not adversely affected by running the relatively long operation. So let's create a Web API project and let's name this project Test Time Consuming Operation Web API. Note that when the Web API project is created, a controller class is automatically included in the Web API project. This automatically included class is named Weather Forecast Controller. Code within this controller simply outputs made-up data representing a weather forecast. We'll come back to this Web API project in a bit and create our own controller class. Let's create a UWP project and let's name this project Test Client Async UWP. Okay, so let's go back to the Web API project and let's create a Web API controller class. And let's name this controller Test Long Operation Controller. So the code in this method is faking a relatively long running operation that needs to be performed before returning a value to the client code. The call to the server-side component's relevant action method will be handled through an HTTP GET request from our UWP project. We'll write the code for this in a bit. Please note that this tutorial is not about UWP or Web API, so I'm not going to go into detail explaining these two types of projects. The focus is on writing code using the task-based asynchronous pattern in C# to ensure that the user's experience is not adversely affected by long-running operations, perhaps being run remotely through a Web API call. So note that we are not only going to use the task-based asynchronous pattern on the client side, we are also using the task-based asynchronous pattern for this action method in the server-side code. We have discussed how client-side UI synchronous code can negatively affect the user's experience, and that implementing the task-based asynchronous pattern on the client side can make the user's experience much smoother. The task-based asynchronous pattern can also be implemented for server-side components like, for example, a Web API component or an ASP.NET MVC component. This creates better performance on the server side, which ultimately can affect client-side UI responsiveness. On the server side, it means, for example, that the thread of execution on which a relatively time-consuming method runs will not be blocked while the relevant time-consuming operation is performed, and the relevant thread can handle other requests while the relatively time-consuming operation is running. In terms of the user's experience, if a time-consuming operation blocks the thread of execution because of synchronous code, this could tie up server-side resources, causing a delay in performance on the server side, and at worst, could cause, for example, a client's HTTP request to time out. So, server-side synchronous code can also adversely affect the user's experience. So in order to fake the long-running operation, I'm simply going to create an await statement and use the task class's delay method to pause the method at this point for 5,000 milliseconds. In other words, it will cause a delay of 5 seconds. Once the 5-second delay representing our long operation is finished, the code returns a string value. So let's return the text Web API long-running operation completed to the calling client code. So let's test the code. And you can see that the output from the weather forecast controller code is written to the browser window. Let's change the URI in our browsers to point to the controller code that we have just created. So let's make a GET request to our test long operation controller. Great! There is a clear delay of 5 seconds before the expected string result is written to our browser windows. Okay, let's write the calling client code in our UWP project. So, we are going to drag 2 buttons onto the design surface from our list of XAML controls. Let's drag our first button onto the design surface. Let's enlarge our button a bit. Let's name this button BTN Local Operation. Let's label this button Local Operation. So let's zoom in a bit so we can have a clearer view of our button. Let's drag our second button onto the design surface. So let's enlarge this button a bit. Let's name this button BTN Web API Call. Let's label this button Web API Call. So let's drag a list view component onto our design surface. You can see the list view is currently the same size as our design surface and is covering the whole design surface. Let's resize it so its contents will appear to the right of our buttons. Let's name our list view component LVW Output. You may have noticed that creating a beautiful design for our UI here is not a concern for this video. But in the interests of saving time, this design will be adequate for what we are demonstrating here. It might be a good time to make the point that UX is not just about aesthetics, which of course is very important, but it is also about performance. We are focusing on how we can write asynchronous code to drastically improve the user's experience. So let's go to the code behind our design surface and let's write a private method named addListItem. And here we are writing a piece of reusable code for adding a string value to our list view component. Within each of our 2 button click event handlers, we want to add relevant string results to our list view component. We'll write the code for the 2 button click event handlers in a bit. Let's create two integer member variables, one named _local operation counter and the other named _web API operation counter. Let's write the code that executes when the button that performs the fast local operation is executed. So we can auto-generate the method signature for the relevant button click event handler method by double-clicking on the relevant button on our design surface like this. So when this button is clicked, we want to increment the _local operation counter integer member variable by a value of 1 and append this integer value to the literal text fast local operation completed. We are adding this string value to the list view component that we named lvwoutput through a call to a private method named addListItem. So let's implement the code to call the web API method that implements the long-running operation. And we want this code to fire when we click the button we have named btn web API call. So let's double-click the relevant button on our design surface to auto-generate the relevant button click event handler method like this. So the code here is a little bit more involved than the code that runs when the user clicks the button we have named btn local operation. Let's first write the code to increment the _web API counter integer member variable by a value of 1. So we are going to use the HTTP client built-in class to make a HTTP GET request to the relevant web API action method. So let's instantiate a HTTP client object like this. The HTTP class is a member of the system.net.http namespace. So let's ensure we include the relevant directive. Let's use a HTTP response message object to encapsulate the returned value, returned from our web API component's relevant action method. So we need to run this line of code asynchronously, which means we need to include the await operator before calling the getAsync method. Note the getAsync method has the async suffix, so we know that this is an asynchronous method. Note the red squiggly line here. This is because in order to run this code asynchronously, we need to include the async modifier within our btn web API call _click event handler method's method signature. Note that we don't need to return a task object from this button click event handler method because this method is a high-level event handler. So we need to pass the URI of our web API action method to the getAsync method, so that the relevant action method is invoked on the server when the user clicks the button named btn web API call. So let's run our web API component by running the relevant web API project. So a GET request is made to the weather forecast controller by default. Remember, this code was auto-generated when we created our web API project. Let's change the URI within our browsers so that a GET request is made to the getAction method within our test_long_operation_controller class. Let's refresh our browsers. And note, a 5-second delay before the expected result is written to the browser window. So let's copy the URI that our browser is currently pointing to. Let's go to our UWP project and let's paste the URI here as a string argument to the http client.getAsync awaitable method. Let's call an awaitable method named readAsStringAsync to retrieve the content returned from our call to the web API component. Then let's write code to add the returned string to the list view component that we named lvwoutput. We can do this through a call to our private method named addListItem. So let's move the code that increments the _web API counter variable to just above where we have added our string result to the list view component. So we need to ensure that our web API project is first running before we run our UWP client code. So let's do that. Let's run the UWP project so we can test the performance of our user interface. Let's first test that we are able to get a result back from our Web API component. So let's click the button labeled Web API Call. Great, the result appears in the list view as expected. The result is added to the list view, and we can see it as output on the client side, displayed within the list view component. Notice that there was a delay before the result appeared in the list view because we want this call to emulate awaiting a long-running operation. Now let's test that when we execute this long-running operation, that the UI thread is not blocked. The UI thread should not be blocked because we are making our GET request to the Web API component asynchronously. So let's once again click the button to make our Web API request. And now let's click the other button several times to run our fast local operation several times. Great, and you can see that the local task is running even while awaiting the result from our remote long-running server-side operation. The UI thread is not being blocked, and our asynchronous code is working as expected. You can see that when the asynchronous operation completes, the appropriate result is added to the list view component. And while we were waiting for the relatively long-running asynchronous operation to complete, we were able to run several local fast operations. So the fast local operations are running concurrently with the long-running asynchronous operation. So let's make several requests to our Web API component, and let's also run our fast local operation concurrently several times. Great, and you can see by the output appearing in our list view component that the user's experience is smooth. The user's experience is not adversely affected when the long-running Web API operation is executed. The user is able to perform other operations using our application without the user's experience being impeded by other incomplete long-running operations. This is why the task-based asynchronous pattern is so powerful. This, in my opinion, is one of the reasons why the C# language is so powerful, because a lot of the complexity in making a long-running operation run asynchronously is hidden from the developer. This complexity is abstracted. The C# language makes the inclusion of asynchronous behavior in our applications easy to implement. Please download the code for yourself and play around with the code so you can experience how the relevant asynchronous code results in a far smoother user experience than if the same code were implemented synchronously. The links to the relevant GitHub repositories have been included below in the description. I hope you have enjoyed this video on using the task-based asynchronous pattern in our code to include asynchronous behavior in our applications. In my opinion, this is one of the most important concepts in C# programming. In an age where smaller devices are used to perform relatively long-running operations, we need to ensure that our users' experience with our applications are not adversely affected by poor performance of our applications caused by synchronous code implementations of relatively long-running operations. We can drastically improve the performance of our applications by running these relatively long-running operations asynchronously. This is now easy to achieve using the C# programming language. Please consider subscribing for more content on advanced C# concepts and much more. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you've gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released on this channel with anyone you feel may benefit from their content. I of course love reading your comments, so please feel free to share your thoughts with me in the comments section. As always, the code examples that were created in this video can be downloaded from GitHub. A link to the relevant GitHub repositories can be found below in the description. Thank you, and take care.